we have given a cyclic graph, right? Directed graph, a cyclic directed graph, and from node n nodes given 0 to n minus 1. So we have to find all the possible paths from 0 to n minus 1 node. Okay, so we have to return in any order. Let's understand. Directed means we have a direction is already given, like 0 is pointing to what, this direction, another node 1, and it is connected with another node 2, and 1 is connected with 3, and 2 is connected with 4, like this. This direction is already given. 1 is going to this, and then 2, and then 2 is going to 3, and 1 is going to 3, like this we have given. So what we have to do, we have to give the direction either this one and this one, right? So sorry, this one and this one, right? Not either, means both combinations we have to do. 1 2 is given, then 3 is given, and then 3 is given, and then empty is given, right? But output is what? 0 1 3, like we are going from this direction, right? And another is what? 0 2 3, like this direction we are going. So all the combination we have to return either this and this, or this and this. Okay, so let's understand the another example, right? So if we have the direction is given, right, all the direction is given, this one 0 is going to here, 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 so it will become very complex, right? So we have to make the combination, and that can be anything, right? But the direction, based on the direction only. Okay, so we'll start from 0 0, then we'll move to what, direction 4, then 0 3, then 3 to 4, like that we have to go. And similarly you can make the output as you can see here. So what is the overview we have? So there is a hint is given that we have a we have the problem, right? And that would be backtracking, since the problem concern about the about the path exploration in the graph, right? We have to explore the path, and so it is a perfect scenario to apply the backtracking algorithm. So what we have to do, we have to understand the backtracking, and then you have to move one by one. Okay, so in this solution we will start from approach using the backtracking, and then we will discuss the alternative approach that can be a DP or something else, right? So DP is the best example if we are using backtracking, right? So let's just start doing the backtracking on the code section. So here I am in the code sections. Okay, so we'll start from here, right? So let's begin. First, what we have to do, we have to understand the algorithm, right? So algorithm is that what we can do, we have to go to DFS, right? Depth first search using the traversal, right? So actually, indeed, often the backtracking algorithm, we have to assume the form of DFS, but the additional steps of the backtracking. Okay, so and for the DFS, we often adopt the recursion as its main form of the implementation. With recursion, we could implement a backtracking algorithm in a rather intuitive or concise way, you can say, right? So we break it down into the two sections at least. That is, first, if we'll talk about, essentially we want to implement a recursion function, right? That is called backtrack, and we have to pass the current node and the path, right? So which that will continue our exploration of the given current node and the path that we will traverse, right? So what we can do, we will do first recursion, right? Within the recursion, we first define its base cases. So the moment that we should terminate the recursion, obviously we should stop the exploration and we will encounter our target node. So the condition of the base case is what? Current node equal to what? Target, right? That is the our base case. When this will come, we have to terminate, right? So as the body of our recursive function, we should enumerate through all the neighborhood of the node of the current node. And so we will for each node, what we will do, we will first mark the choice by appending the neighbor node to the path, and then recursively invoke all the backtrack function to explore all the deeper. And at the end of the iteration, we should reverse the choice by popping out of the neighbor node, and then we'll move to the path, from the path, you can say. So we should we should start all over the next neighboring node, and then we define our backtracking function. It is sufficient to add all the initial node, but let's say we'll do the backtracking function exploration. Okay, so let's begin. Okay, so what we will do, we will first take what int target, right? We'll take target, then we can take this is our target, right? Because we have given the graph we have already given, right? So we'll take target. So what we can do, we'll take let's see, I'll do as we should use private, right? And then we will use same as private, will take private, and then we will use int, and this is what, this is our graph. The graph is already given, right? You can see. So these things will take our, where will take out outside our main method, right? And this is our class level, this is our instance. So sorry, instance variable will say, and this will we have to initialize, right? So what we will do, one more thing we should take, that is our, we can say result. We have to return the result, and this is what type, this is a, because why we are taking outside, because we are doing recursive, right? And the recursive, these results and the values should be changed based on the each sub problems, right? And so that we have to take all the things outside this one. I'll take this private also here, right? Three things will take: target, graph, and result. Now what we will do, we will first make the base case, right? What is our base case? Base case is what, we have to take if current node, right? What is our current node? So we have to take the function, right? We will not directly take here, so we have to make a function, another function, and that is called our recursive. We can say we will take a recursive function, that is, or either we can give the name backtrack. This is our backtrack function. Okay, and this backtrack function will take what, two things. First we'll take current node, we'll say current node, and then another, it will take linked list, right? And this linked list is what, integer type. Okay, and this is nothing but what, linked list of path, right? A list of path, you can say. So two things will pass, current node and the path, and it should return what, nothing, that is void, right? And we'll take we will take what, modifier, we can take as protected modifier. So we were talking about the base case, right? So we'll put this base case here, this is our base case. So if current is what, if current node that we are talking about, this one, current node is what, equal to this dot what, target, right? This dot target. And then if that is the case, right, then what we have to do, if that is the case, what we have to do, let's see. First you let take a note, right? What we have to do, one should make a deep copy of, one should take you can say make, right? One should make, not take, you should make a deep copy of the path, correct? If current node is target, then how we'll do that? First you should do this dot result, this dot results equal to what, we have to add in that, right? We have to add we will take a slice value, new, we'll take array list, and the array list will type of integer, correct? And this is, we can say path, right? So the path that we are passing, that we have to add onto the result, right? That we have done here. This way we can do. And finally, if that is the case, we are not going to do anything, we have to break, means we have to return, you can say no operation is required now. But if that is not the case, if this is base case is done, right? But now we have to, what we have to do, we have to explore the neighbor, right? We have to explore the neighbor. Neighbor, you can see the what we can say, a spelling mistake. So explore the neighbor nodes, right, after another, correct? And then what we will do, we will do like, we will make a loop, right, to explore the neighbor. How we'll do that? First we'll take next, we can say next node, not next, sorry, next node. This is our next node, and this will come from where? Will come from graph, right? Will come from graph. And graph of what? The current node, right? This will come from here. Current is what? Current node, right? Yeah, current node. Then what will happen? Now we will explore all the node now, right? Now we have to mark the choice. We have to mark the choice. How will do that? Before backtracking, right? Before backtracking. So sorry. Now what we will do? We have to mark the path. How we'll do that? We have path, then we will do add last, right? There is a method add last. In the add last, we'll add next node. This is our next node, right? We have got. Now we have to mark it. So we'll do this like, okay. Now we have to do this dot backtrack, okay. This dot backtrack we have to call internally for the next node, right? So we have to pass the next node and the given path we already have, right? That we will pass. So it will backtrack, right, one by one. Now we have to remove the previous choice, right? We have to remove the previous, we have to remove the previous choice, right? To try the next choice. Either we will go like this path or that path, that we will do that. How we will do that? Path dot remove last. That last we have added, that we have to remove last, I think. Remove last. Yeah, we have last. Yeah, we have. Then we will do remove last, and then we will remove the previous choice, and now we have to try it for the next choice, right? That we have done. Now this function is our backtrack, right? This function we have to call where? Here, right? In all paths we have to call here. So for that, what we have to do? We have to go one by one, right? How will go there? First of all, we should do, right, this to target, right? We have the target, this dot target, we have target here, and this target is what? The graph we have given, graph dot length, right? We have graph dot length minus 1 we will do, right? Now we have to update our graph, this dot graph equal to graph, right? We are doing setting, right? We are setting the value. So this dot result will call, and this is what? Equal to new, we are initializing the array list we have taken, right? We can take like this, not from there, here to here, okay. New array list, right? We will take the list, but this array list will contain one more list, right? Here at the time, this is what? This is the type of graph, right? So you can take like this. This is our result. Yeah, we have taken here result, right? Similarly we'll take that, right? This is our result. We have initialized our result, or we'll say that we'll take like this also. This will work, this will work, right? So now what we can do, now result is updated, graph is updated, and target is updated. Now three things are updated. Now we have to adopt what, we have to adopt the linked list, right? So we should say linked list for the fast access, you can, for the fast access, you can say, for the fast access to the tail element, right? Okay, now for this what we have to do, we have to update the path also, correct? So path is given or not? No, path is not given here. So we have to get the path, you can say, because we have to call this one, right? We have not updated the path, so we have to update our path. How? Like this only, we can say new, using new keyword, right? New, will say new, and then we'll do this one, right? Now after this path is now initialized. Now we have to add what, path dot add last, right? At last what we will add, we'll add 0, right? Now we have to kick the backtracking here, right? You can say kick off the backtracking and starting from the source node, that is 0, correct? And so what we have to do, we have to call this dot backtrack, right? This dot backtrack, and we will start the source node and the path we have to pass, right? And after the backtracking will work, then finally what we will do, we will return this dot the result, right? This one. So let's summarize again what we have did. So if we'll start from here, we have taken target, graph, and result. So why we call result is like this only, right? Here. So we'll take, we are passing the graph, right? From the graph we will initialize our target, graph, and result. We will initialize. Then we will initialize our path also. We will add our path as a last 0. And what we will do, because this is cyclic, right? So we have to did this, and then we have to start backtracking from 0 index, 0 node 0, and we are path, giving the path. So from 0 we will do that, right? Now what we have to do, we have to backtrack this function, right? So we have already created this function in which we are passing the current node and the path. So if current node is equal to target, right? Current node is equal to target, do not need to do anything, just add all the things over the path. We have the path, right? That we will add onto the result. The current path we will add onto the result, and then we will return that. If not that the case, what we will do, we will move to the all the neighbors, and one by one we will add to the path, and we will backtrack the path, and then we will remove the remove from the path. First what we will do, one by one we will add the next node, and we will backtrack next node to the next node, and then we will remove the path. Okay, finally. So in this way we will do our implementation. Okay, so this is our backtracking approach, in which if we'll talk about the complexity, right, analysis. Let me run first, then we will talk about the complexity. So this is our void function. Oh shit, I think we have did something wrong. This is, we are taking void function of error, cannot find the symbol. Why what is the function? Linked list. Yeah, a spelling mistake. Linked list. Let's see where I have written L should be in capital. L should be in capital. Correct. Yeah, these functions also taking linked list. This should work now. Yeah. So if we'll talk about the complexity, right? So let n be the number of nodes in the graph, right? So first of all, let's assume, or you can say, let us estimate now how many ways there are at maximum to travel from 0 to 0, node 0 to n minus 1 of the graph, right? Say we are going now here n minus 1, right? How many graph we have given? So we are starting from 0 to n minus 1, right, with the n nodes. So let us start from a graph with only 2 nodes. As we can imagine, there is only one path that is correct, and only 2 paths in the graph, right? So what we will do, we will move to one path that is our correct path, new path, and there is another path that we have talked about, right? And so the time complexity is what? 2 to the power n, right? Because when we call at most 2 to the power n minus 1 possible path we will get. Okay, and for each path there could be at most n minus 2 iteration for the intermediate node, and it will take O n time to build the path. So we can say that it will take 2 to the power n path time complexity, and space is O of n because we are taking only extra space to store the value, to store the path value, right? So we'll discuss the time complexity in another approach too. So another approach will talk about the top down approach of the dynamic programming, and we'll see that. Okay, so first let me submit this one, then we will talk about the another approach in the other part of the video. Okay, so stay tuned for the another part of the video. Thank you guys, and we will see you on the another part of the video.